It's a pleasure to be here and an honor to be able to tell you about the search for dark matter with the XENON project. The project is, the goal of this project is to find dark matter particles as they scatter in this material which I love, which is xenon, liquefied xenon. And we'll try to do this by building and developing instruments, detectors, which are ever more massive and at the same time ever more quiet in the sense of noise, because the signal, as I will show you, is extremely rare, of course. And so we have been inventing ourselves in making these detectors better and better for the past 15 years. And as we improve the technology and the experiments, we continue to be hopeful to find a signal. So far, as David said, we have just excluded orders of magnitude in terms of the interaction with which these dark matter particles care to do something with the standard matter of which we are made. But as we move forward, I have not lost hope, so we keep searching as we build the next yet experiment, which I will show you towards the end. And at the end, I never felt more excited that finding nothing today is actually as important as to find a signal, because we either will, hopefully in the next 5-10 years, we'll find this damn signal finally, even a glimpse of it, or we will exclude, or we will find what dark matter is not. And that's equally essential, because we will drive theory to search somewhere else, to find answers in other direction. And so that's the goal of the project. The question of the nature of the dark matter which prevails in this universe remains a mystery. It's the question we are trying to answer, at least with our experiment. And it's a fundamental question which connects physics, fundamental physics, cosmology, astrophysics, and how can we resist not to find an answer to this question when we know that the universe is actually dominated by this form of matter? The matter of which we are made of, the standard matter, the atoms that we know, is only a tiny fraction, only 5% of the matter energy density of the universe is in normal matter. So, in fact, this dark matter which prevails is the glue which keeps the universe together, because from our own galaxy, you saw that picture in the first slide, from our Milky Way to every other galaxy, from clusters to the larger scale structures that we observe, the gravitational attraction due to dark matter is what keeps everything together, is the glue which keeps the universe together. And perhaps the most direct way that we have to see dark matter, the presence of dark matter, is through this phenomenon of gravitational lensing, the distortion of light due to the presence of mass. And in fact, last year, the Dark Energy Survey, studying the distortion due to weak lensing of 26 million galaxies, has come up with the first and very detailed map of dark matter distribution. And what is amazing, and so this is the left plot here, the region with the reddish color are regions, structures where dark matter is more prevalent, and the blue has less dark matter. But what is relevant in its first map, which is just a piece of the sky, is that the growth of these structures from their moment of formation to today can actually be nicely explained by cosmological models which are the basic cosmology, which is based on the fundamental theory of particle physics, on the standard model, on precision cosmology, through which we know precision cosmology in the last 20 years has given us an amazing amount of information about the origin, the evolution, the expansion of this universe. And we know from this precision cosmology that these two dark components of the universe, the dark matter on one hand and the dark energy on the other hand, we know these two dark components with high precision. Unfortunately, what we don't know is really their true nature still. So we remain unclear about the nature of these dark components. And while the next generation cosmological survey, with their increased capabilities to trace the evolution of the universe, will hopefully give us an answer on the dark energy question, if it is a cosmological constant, is a new dynamical field, or maybe we have to change general relativity. I think the answer to the other dark question, what is dark matter, will, yes, come a bit from cosmology, but also directly from experiments on Earth, such as our experiment and similar experiment, or from experiments at accelerators. Together, the synergy of these studies hopefully will help us understand the nature of this dark matter in the next decade, and dark energy. So before I move on, I mentioned this ordinary matter. What is worth to point out, especially among us as we look at the night sky, actually the 5% which constitute the standard matter, as we say, is really not all what we see. What we actually see in stars, in planets, everything which emit light at some wavelength, is actually only 1% of the total matter in the universe, because the rest is in gas, mostly hydrogen, helium, which fills the halo of this galaxy, every other halo, and all the spaces between these galaxies. So only 1% is actually what we can see, which is actually daunting. The 85% of the matter in the universe is invisible, or we say it's dark, and we say it's dark because it doesn't emit or absorb light at some wavelength that we can see. The big question is, finally, I told you already, what's the big question? What could this dark matter be? And one of the, despite this prevalence, 85%, as I said already, we have not directly seen it. What could it be? An attractive idea, a leading hypothesis that dark matter is a thermal relic, something which has been left over from the early phase of the universe, when it was 1 billionth of a second old, after the Big Bang, sorry. So when it was about 100 GeV or so hot at that very high temperature. And while no particle of the standard model is a viable candidate for dark matter, the universe, the young universe, was hot enough to produce these massive new particles, which we are here hoping to detect in the laboratory on Earth. So a relic of the Big Bang. And if these relics are there and they're stable, if they're stable, they can still be around today and fill the halo of the Milky Way. And from the amount of dark matter in this Milky Way, we can infer how many of them, of these particles, can reach our detectors. But I wanted to also point out that while we talk about this class of relics, we refer to them generically as weakly interacting massive particles, or WIMPs. The class of WIMPs is just one candidate of dark matter. It has been very popular. As you can see from this plot, the height of the thing there is how many papers have been associated with this specific candidate, but it's not the only one, the WIMP class. It's very well motivated theoretically, because many theories behind the standard model give us naturally WIMP candidates, such as the lightest supersymmetric particle, the neutralino in supersymmetry, or the Kaluza-Klein photon in extra dimension. So the WIMP has been really favored for many, many years, and is not yet dead. We're looking desperately for it. But as you can see, we have particles which span a huge range of masses. This is the dark matter candidate mass in electron volt, and you go from fuzzy dark matter, which is unbelievably tiny, to the axion, for which is also well motivated, for which a lot of nice searches are going on today, to even primordial black holes. So we have a huge range of particle mass. I'm not showing it here, but also their interaction strength is completely wild. It goes everywhere. So as an experimentalist, if you ask yourself, so how do I look for this dark matter particle, any particle, you have no idea where to look. You have to trust one of your theorist friends, or, in my opinion, the best thing that we can do is to search in a region where we have the best technologies to to tackle the problem. And that's what we have been doing with the XENON experiment. So, in fact, the way that we have been searching for WIMPs until now has been in three directions. We can either expect to produce these new particles at accelerators. We have the Large Hadron Collider in Geneva, the highest energy luminosity machine that man has ever built. So we hope still that new particles are produced at the LHC, and we search desperately for this new particle through missing energy, monojets, and whatever. However, even if a new particle is found at the LHC, it's clear that associating it with dark matter is going to be challenging. How do you know that it is the dark matter? We're also looking for dark matter through the products of standard model particles from the annihilation of these dark matter particles in dense regions of the cosmos. So through neutrinos, through gamma rays, we have the Fermi satellite in space, through the antiparticles, through the AMS spectrometer on the space station. And finally, we have been looking for dark matter through direct detection, which is the topic of my talk and more experiment. Directly searching for the interaction of this hypothetical WIMP particle, which is shown here, as it scatters off an atomic nucleus, an idea which was put forward in '85 by Goodman and Witten here. And so the idea is very simple. If these WIMPs fill the halo of this galaxy, although rarely from time to time they care to scatter off a nucleus of an atom, and we can calculate the energy which is imparted to the nucleus. It's an elastic collision. And that energy is the first challenge that we face as an experimentalist, to try to see this dark matter particle through this process, because the energy can be calculated to be very tiny, a few tenths of electron volt or less, depending on the target. So the observable is this kinetic energy which is imparted to the nucleus. And before I move on, for now, for a long time, we have been talking mostly of elastic scattering of a WIMP off the nucleus of an atom. And through this process, we have been searching for many physics models, WIMP interaction, such as the spin-independent dark matter scattering, because there the coherence of the scattering over all the nucleons is relevant. Or we have been looking for the scattering of a WIMP, the coupling of a WIMP through the spin of the nucleon. And in xenon, for instance, we have many isotopes which have spin, and so on and so forth, and many other, also pion coupling, WIMPs through the pion coupling process. However, I want to point out that more recent here, detectors such as ours, which give us both nuclear recoils and electronic recoils, as we call them, are able also to search for WIMP interaction, non-standard WIMP interaction, such as dark photons from the dark sector or axion-like particles, super WIMPs. We look for the energy which is imparted not to the nucleus of the atom, but to a shell, an electron of the atoms, or a combination of the two. For instance, we have been looking for inelastic magnetic dark matter in Xenon 100. Okay, so that's just something to point out. The first challenge was the small energy. The second challenge of direct detection experiments is the extremely low interaction rates. How many events we expect to see in a detector if we build one to search for it. And here you see it because the differential rate, the amount of events that we expect, is proportional to how many nuclei, how many atoms I have, how many targets I have, and is proportional to the density of these WIMPs in the halo of this Milky Way, and also to the velocity distribution. How do they move in this galaxy? And it's also proportional to the cross-section, the interaction cross-section, which we usually take from some theoretical model, d sigma der, and of course is inversely proportional to the mass of the particle. So that's the basic equation which gives us the rate, simplified. So if we plot or calculate the rate, and this is shown in events per keV, unit energy, unit mass, in this case ton, 1,000 kilograms of stuff per unit time in 1 year. Here is shown the rate as a function of recoil energy, the observable that I can measure, for 3 elements, 3 targets: the xenon, germanium, and argon. These are 3 leading target candidates for dark matter direct detection. And the calculation, you have to assume a cross-section and a mass. Here is done for every WIMP, let's say 50 GeV particle, for a cross-section of 10 to the minus 46 square centimeter. That's a very tiny cross-section, but that's close to the level that we have been excluded so far with our direct detection experiment. And what you see, the message here is that this rate falls off exponentially. And in xenon, the red curve, you have many more events compared to the other targets, because xenon has a big atomic number. At 131, it has a lot of nucleons. The scattering is coherent over all these nucleons. And so if the threshold, if the limit of energy which I can sense with my detector is low enough, in this case 10 keV nuclear recoil, I could, and if the WIMP interacts at that cross-section with a 50 GeV of mass, I would expect in my detector 15 events in my 1 ton of detector if I wait for 1 year. So it's a 15 events per year in 1 ton, which is already quite daunting compared to the overwhelming rate which comes from backgrounds of different types that I'll tell you in a moment. The other thing that you want to notice from this slide, on the right-hand side is the same calculation, but now it's for a low mass. We have been searching recently much more in the low mass region, sub-GeV or GeV particles. Here is for a low mass 4 GeV WIMP. And what you see for a cross-section 10 minus 40, that the rate falls even more steeply for xenon, definitely for a low mass particle, a lighter element such as neon shown there in pink or whatever is the name, and silicon, for instance, are more appropriate to scatter such a light particle off. So the second challenge is this extremely low rate, few events, maybe 15 events per ton per year. And the last, for me, I think, the holy grail or the most important challenge of this experiment has been and remains to actually find this signal in a sea of background. We are not just waiting for the WIMP to give us those few events. We have events from radiation of all kinds. And so the first thing is that if I place the detector in this room, I will be bombarded. The rate will be overwhelmed by the rate induced by cosmic ray muons. And so that's the first reason why these experiments are placed deep underground in appropriate laboratory under kilometers of rock, or in a mine, in a deep mine, so under the surface of the Earth, to shield ourselves from the muons, cosmic radiation, which is attenuated by depth. And so even if we go deep underground, we have the last enemy. One of the enemy of this detection is neutrons, which are induced from these muons, because even as we go deep, they're not completely killed, these muons. So we have neutrons from muons. We have neutrons from materials radioactivity. Everything we use and build, we use to build these experiments is radioactive. We are very radioactive. And especially now, I'm very radioactive. When I talk, I'm more radioactive than ever. So we have radioactivity from materials, and in terms of neutrons from spallation or from alpha N reaction, that's another enemy that we have to fight. And I'll tell you a little bit how we do that. We have also from from radioactivity, we have also other type of radiation, potassium-40, cobalt-60 in the steel, all kind of radioactivity, gamma and beta emitters which come with our materials. And ultimately, we have neutrinos. Neutrinos from the sun, atmospheric neutrino. We have hopefully supernova neutrinos sooner or later coming into the xenon detectors. And so these neutrinos constitute our ultimate background, because we cannot do anything about it. So we cannot shield ourselves from this neutrino. In fact, they will become our signal, and that's my dream. We often call it the ultimate background of these experiments as we move forward. But for me, it gives me the hope to see a signal, because it would be phenomenal at least to see a signal from solar neutrino through coherent, for instance, scattering in xenon. So this is the key challenge, and there's been really an effort of the xenon and every other experiment to reduce the amount of both radioactivity, to search for low radioactive materials. You can imagine if I'm building a vessel which contains my xenon, I need to search for the steel, which is, if I use stainless steel, I have to beg company, producer of stainless steel, to let me measure and try plates after plates after plate until I identify the lowest activity cobalt-60 stainless steel, which I can use to build my vessel, and so on and so forth. Every nut and screw that we use in the xenon experiments has been screened, as we say. We measure it with high sensitivity germanium detector, with neutron detectors, to estimate their level of background and therefore predict how much rate we can get from that radioactivity. It's been painful, but we have succeeded, as I will show you, to achieve the lowest background in any dark matter detector to date. So for me, that's the greatest challenge. The sum of all these things that I told you so far, and I'm taking too much time already, is that detectors have to be massive. The more N, the more atom, the more target nuclei or atoms you have, the better. So massive detector with very low energy threshold to seize the rate, which is highest at low energy. And you have to have very low, very quiet detector, very low background, as we say, detector. And so people have been inventive in using a variety of techniques and a variety of materials to search for this dark matter directly in the laboratory. What we are looking for, again, is how to detect the energy which is deposited in a target by a dark matter particle. And when you have radiation in most material, what happens is that you can excite the atoms of these materials, and through the excitation you have scintillation, light. You produce ionization electrons, so you have charge, and you also shake the crystal. If it is a crystal form, you produce, if you like, heat or phonon, and that's another channel. And the majority of the experiments which are listed here are using two of these signals, either charge or light, or just charge and phonons, to make the best out of the detector, because, as we said, the key is to have as many handles to understand signal from background. So there is a large number of experiments which is either are running, have been operated in the past, but the key is that the liquid xenon-based detectors have maintained leadership and have been at the frontier of this field. And this is a plot both for a 5 GeV WIMP cross-section and a 50 GeV WIMP cross-section, a plot of the sensitivity, if you like, or the cross-section as a function of time. And as David, I guess, alluded to, we have been able to see orders of magnitude in this cross-section, excluding WIMP interaction, spin-independent type, over the years, over the last 10, 15 years, by orders of magnitude. And so the reason why, compared to other technologies, so why is this xenon so favored and so interesting for dark matter detection? There are many reasons. I could talk only about that for an hour, but one of the key reasons right now is, of course, the scalability, the fact that we have been able to make massive, more and more massive detector. The reason is that xenon, when we liquefy, has a very high density, 3 times the density of water, and so it enables you to make, in a compact detector, a homogeneous large mass. Put thousands of kilograms together without too much headache, also the very cost-effective way compared to, let's say, semiconductors. The scalability, because of the density, also xenon has a very high Z, a Z of 54. So the Z and the density of this material enables us to gives it a very good self-shielding ability. Namely, you need only a few centimeters of this stuff, of liquid xenon, to absorb penetrating radiation. The self-shielding ability of liquid xenon has been fundamental in reducing the background of these detectors. And so the low background feature of liquid xenon detector comes from the self-shielding from the feature of the signals that we detect in xenon, which enable us to select the two type of interaction from electronic or nuclear recoil, and also specifically the 3D imaging capability of the type of detector that we have built. And of course, with this xenon, we can have a very rich physics program, which I mentioned briefly before. The most fundamental reason, I would say, of course, is also the technology is mature now. We spent 15 years, so today, it was unbelievable when I started with my first proposal to the National Science Foundation for the XENON project. It was a 10-kilogram detector. The fact that we're here today building an 8,000 kilogram detector is actually quite surprising to me too, because my proposal called for a Xenon 1 ton made of 10 cloned Xenon 100, because I couldn't imagine at that time, 15 years ago, that we could build a 1 ton detector in one single unit. So the technology is mature, and many technology, how to handle all these hundreds of thousands. You need 500 liters of xenon gas. Xenon is a noble gas. It's extracted from the atmosphere. It's another talk in itself. And so you need to clean it. You need to purify to make it viable as a target material and a detector material. So we have matured the technology to handle this large amount of xenon, to purify it and keep it clean and cold over years, because we are waiting for this rare signal. We cannot have an experiment which lasts just 10 days and 1 month. But the most fundamental reason why xenon has been, what did I want to say? The love of my life, but it's almost the love of my life. It's an amazing material for detectors. And the reason is that it has the highest ionization and scintillation yield among the all noble liquid. And the way that this light and charge is produced in liquid xenon is it's a very complicated mixture of processes. When you have a radiation, let's say a WIMP or a neutron kicking a nucleus of an atom of xenon, you're going to excite these atoms and molecules, and through the de-excitation of these excimers which are formed, you get scintillation light. And these scintillation photons are very prompt, few nanosecond timing, and very abundant, very high yield. And they are, however, unfortunately, in the very deep UV, 178 nanometer, which has presented a challenge over the time to find the proper photodetector to see it. You cannot see it with the standard photomultiplier. So you produce scintillation light, but at the same time, when there is energy deposited in xenon, you also produce ionization electron. You ionize the atoms, and these ionization electrons, if they get freed from their parent ion, they can be available for you to detect as a charge carrier. However, these electrons like to stick to their parent ions. They recombine with their parent ion, and the recombination process is very complicated. Depends strongly on the type of particle, on the applied electric field, but through the recombination process, actually, you end up forming the same dimers, and again, the excitation gives you scintillation. So the scintillation light in xenon actually comes from two sources, recombination and direct excitation. And some of the energy goes into elastic nuclear scattering, and we don't detect so far the heat. The key has been to use this signal, this response of xenon to radiation in a type of detector which is shown here, a so-called two-phase time projection chamber. Essentially, this is a 3D imaging detector. 3D imaging means that you can see in X, Y, and Z in space everything which happens inside, let's say generically everything, on an event-by-event basis. And imaging capability, as you know, gives you a lot of power when you can see things. It is homogeneously filled, because, I mean, you take a container and you put this purified liquid in and you keep it clean. And so if you have an interaction, if you have some energy deposited, you have this flash of light produced by the scintillation. And you also have ionization electrons, which are free. If they're free to move, we apply an electric field to move them across the liquid against the field. And the key is to use the appropriate photodetector to see this light and the charge. The trick of the two-phase, two means liquid and gas, has been an intrinsic amplification of this system, because the electrons which reach the liquid-gas interface are actually extracted easily from liquid to gas by an appropriate strong field in the gas. In the gas, they are exciting more atoms and emitting more light. So we end up detecting both the light and the charge through the same photodetectors. One array of photomultipliers below the cathode here, deep in the liquid xenon at minus 100 degrees C. So these phototubes are not the standard one which you have in your lab, because they have to stand low temperature, some pressure, and they have to be sensitive to 178 nanometer. And they have to be low in radioactivity and many other things. And so one array below and one array in the gas. And from the pattern of light in the top PMT arrays, from that pattern of light, how light distributes there, we can infer the X and Y position of the interaction. And the third coordinate, the Z, comes from the measurement of the drift time, the time that the electrons take to drift, because we know the drift velocity of that field. So that's where we have 3D imaging. And we also have, of course, an additional handle in this detector, which is the, bless you, the discrimination between nuclear recoil and electronic recoil from the ratio of charge to light. The S2 over S1 signal, as is shown here, depends strongly on the type of particle. It's very different for a nuclear recoil than for an electron recoil. And that's our additional discrimination. In fact, one of the, oh God, it's late. One of the first questions that we had when this xenon experiment was proposed a long time ago was how many electrons, how many photons are produced by WIMP recoil, by a nuclear recoil in liquid xenon, because I had no idea. I had been studying, as David said, for gamma ray astrophysics, the application of liquid xenon to hundreds of keV, MeV gamma ray from the stars, from supernova, had nothing to do with this few keV of energy that we attempted to see. And so it has been a huge effort over the years. You see the first paper, Aprile et al., 2005, which is more or less the beginning of the xenon project. That was the first attempt to measure this light yield. What we are showing here is photon yield. I mean, how many photons per keV, per unit energy, you can expect in xenon as a function of nuclear recoil energy. And the right plot shows you how many electrons per unit energy can you expect from the same energy nuclear recoil. So a lot of effort. The blue line is actually from the xenon 1 ton itself. It's amazing that such a big detector has given us such a precise measurement of this fundamental quantity. And the message, the thing that you might want to take away is that a 5 keV nuclear recoil, which is that famous threshold that we aim at, only gives us about 25 photons and 25 electrons. And I don't know yet of any amplifier, charge-sensitive amplifier, which can see 25 electrons. That's why the trick of the two-phase amplification is very important. But this is the size of signal that we're dealing with. And another picture, again, an example taken from xenon 1 ton, is the power of this visualization. This is showing Z versus R squared, if you like, if you have a volume of xenon, like in xenon 1 ton, with 2 tons of material in the active region, we can actually, by measuring the X, Y, Z of every event, fiducialize the volume, as we say, select only a region of space which is quieter, which is less filled with background. For instance, the yellow region here represents the 1 and 2 sigma probability for events to be neutron-like, which we don't want. And therefore, the search for dark matter with the xenon 1 ton detector has been limited to this 1.3 ton volume, which we have further segmented with the purpose specifically to reject surface events and neutron-like events. I'll come back to the search. And finally, one more slide about the power of imaging for handling neutrons. I said the ultimate enemy at the end of our WIMP search is a neutron. A neutron does exactly the same thing in the detector, with one big exception. The neutrons have a mean free path of about 10 centimeters. So the larger the detector, the better it is actually, because I can recognize, if I can see things, I can recognize the multiplicity how many scatter the neutron does in the detector, and therefore say, oh, this cannot be a WIMP, this must be a neutron because I identify multiple scatter. And in XENON 1 we have done this study of single versus multiple scattering, which are more abundant because the detector is already quite sizable. And you can see the multiple scatter event, as is shown on the left plot, are concentrated near the top and the bottom of the TPC, where we have a lot of materials, such as the PMT arrays. But also we have identified quite a different distribution of these multiple neutron scatter events with respect to the standard single scatter events, as is shown in the right plot. The S2 over S1 response to multiple scatter neutron, shown in purple here, is quite different. So we have a handle, and the larger the detector, the better. All these features have enabled us to make this impressive evolution of this TPC with time, but it's nice to see it in this plot because what you see is actually from XENON 10, the first prototype with a 5 kilogram of fiducial mass, to the XENON 1 ton detector with more than 1,000 kilogram of mass. However, we would have not won anything just by making it larger and more massive. We have seized the first place by reducing the background correspondingly to the lowest level that has ever been measured in a dark matter detector. This is 0.2 events per ton per kV per day. So it's a handful of events per year. So it's very impressive. This is another way to see it, but maybe I should move on, because here you see the same background rate, which is important, compared to other technology, other experiment. You see the level of XENON 1 ton rate with respect to the initial very hot, as I would say, XENON 10 at the top, but also compared to other low background by definition experiments such as Borexino, neutrino, snow detector, or even neutrino-less dark double beta decay experiment, which by definition have the lowest background so far. So, and one key, the right plot shows how we have managed to reduce this radioactivity in XENON 1 ton, which ultimately is dominated now by intrinsic radioactivity such as krypton, radioactive krypton, or radon. In the xenon itself, you see how through the distillation of the xenon with this cryogenic column, we have been able to reduce the rate at the beginning of the start of XENON 1 ton. In the blue line, the blue data is the rate at the beginning as a function of time as we distill or purify, if you like, the xenon from krypton. We have been able to reduce the krypton level to the sub-part per trillion level from the part per billion that we had initially. That has been key to get to the point where we have been with XENON 1 ton last year. So that's an overview of the program. Just as a function of time, you can see the XENON 100 has operated for more than 8 years. And so we just stopped the XENON 1 ton experiment at the end of December last year. And so we started with 10 to the minus 43 square centimeter as a great success of the XENON 10. We really awoken the world. I mean, we really shook the colleagues and people. How can this little detector in a few months of time achieve such a great sensitivity with respect to semiconductor, for instance, searches? And now we are today at almost 10 to the minus 47, and we are going to xenon n-ton in the next 5 years with an 8,400 kilogram detector. All this effort, of course, as David also said, has been great to work with all these people, which right now the collaboration consists of 170 scientists from about 23-something institutions around the world, and a lot of PhD students, postdoc. And the thing that I'm most proud of, actually, is that a lot of these phases are now the current PI of XENON at some institution, but they were my graduate student and my postdoc here and there. I've been very successful at moving them around, at keeping them within the collaboration, because once they become experts, it's very hard to find experts in this specific field and technology. So we have been very successful in keeping a lot of our experts within the collaboration, moving them from institution to institution. it's a pleasure to work with these people. And the experiments have been carried out at this amazing laboratory in central Italy, the underground laboratory of Gran Sasso, under the peak of the Gran Sasso mountain, about 150 kilometers from Rome or so, where we have the largest and most beautiful laboratory for underground physics worldwide so far. It's a large lab with 3 main caverns. These caverns are cathedrals. These are 100-meter long, 14-meter tall spaces. Xeno 1 ton is in the old B, in the central cavern. You have this, okay, I don't have time to talk, but it's a great place to work. Essentially, it's a drive-through because you have a tunnel. It's under the two-way tunnel, so it's like going, not like going to Colombia, but it's a very easy way compared to a mine environment to work in this surface direct access laboratory. Great place to work. This is an overview of how Xeno 1 ton looks like if you were to visit the Gran Sasso lab. So essentially you have the central detector filled with liquid xenon, and it's immersed in a tank filled with water, 700 cubic meter of purified Ferrarelle type water, in the sense, but the water is being used because despite the fact that we are 1,400 meter below the surface, we still have a lot of muons. So we use water as a cost-effective and great way to further shield ourselves from cosmic radiation. The water is implemented actually with photomultipliers to be used as a water Cherenkov muon veto. Central detector inside the water shield. In this tank, when you come, you see 10-meter diameter stainless steel tank, 10-meter tall, and next to it you have a 3-story building. And Elena had this great vision to make the wall transparent so that people could see the beautiful stuff that we built, which we need to operate the experiment. On the ground floor, we have this 2-meter diameter high-pressure sphere that we use to store the xenon. The krypton distillation column is on the ground floor. Middle floor is the DAQ room, and on the top floor is the cryogenic and purification system, and my group has been specifically involved in the storage and in the purification and cryogenics. The detector looks like this. Essentially, it's a 1-meter diameter, 1-meter drift TPC. You see a lot of white stuff, and yellow is the copper for shaping the field. The white is Teflon. We use a lot of Teflon as a reflector for the VUV and as an insulator. The 2 array of PMTs, top and bottom, appropriately disposed so that we can get efficient detection of S1 and S2 on the top. And you can see the typical WIMP. If we ever will discover a WIMP, the signal will look like this. This is the amplitude of the signal as a function of digitization time. But essentially what you want to notice is that the amount of signal that we can see is actually corresponding to 28 photons or maybe 10 electronic charges. So we have been able to detect very low level signal with Xeno 1 ton with this DAQ. This is not to brag, but this is to give you a sense of how xenon, of course, that detector needs to be enclosed in a vessel because we fill it with liquefied xenon, which is called a -100. We use a double-walled stainless steel, specially procured cryostat, and that's me, of course, to give you an idea of the size. This is one of the dome, and you also notice that the outer vessel for insulation is much larger than needed because we had the vision to go to the next phase, xenon N ton, in an easy way. And all of a sudden, I convinced everybody in a meeting at Columbia that we had to make it bigger because then I could do what we're actually doing, xenon N ton today. So that's the cryostat. Insulated is a thermos because we have this liquefied 3.2 ton of xenon are needed to fill the detector, and out of which 2 tons are active inside that structure, white and copper. As I mentioned, this inside is water shield. This is just a picture of the cryostat closed with the TPC inside in the center of the water. Of course, we fill the water, we put the phototube, and this muon veto is actually very effective, has been working very nicely, giving us, protecting us from this cosmogenic neutrons from muons to the level of less than 0.01 event per ton per year. So we don't worry too much about, at least at this phase, from this background. It takes about 600,000 liters or more of xenon gas, as I mentioned, to make this 3.3 ton of liquid. And so we had to develop custom plants, cryogenic plants, to handle this material. And as I mentioned, my group has been specifically involved with a lot of R&D through Xenon 100 and demonstrator at Columbia in the development of the cryogenic, of the purification, and also in the development of this storage vessel. We don't want to handle hundreds of bottles. We put all our precious xenon, which is the second most expensive, or maybe the first most expensive item of the experiment. It's about almost $2,000 per kilogram today. And the price of xenon fluctuates with the market because xenon is a byproduct of distillation. Industry or economy requires steel. Steel requires oxygen, which is extracted from the air. Xenon is just a little amount because it's very little abundant. But it goes up and down just like the stock market. But today is about $2,000 per kilogram. So not an easy, and not a cheap thing. So we store it in this beautiful sphere. This, again, some pictures just to show the cryogenic system developed at Columbia, the sphere, the krypton distillation column, 5-meter tall distillation column, which has made which has done an amazing job in getting the krypton down to the level that we needed. And this is, again, us, because it is the Columbia group which has developed the cryogenic system, and so it's me with my student and postdocs. The next is just to show, again, probably the level of background which is relevant for our dark matter search in the low energy region as a function of time. This has been possible thanks to this stability and reliability of these cryogenic plants that I showed you before. If we didn't have a very stable system, cryogenic purification and so on, we wouldn't have been able to measure continuously over time the background rate in this detector and accumulate dark matter data. And you can see mostly this amazing low background. That below 25 keV, you have 82 plus or minus 5 events in 1 ton per year per unit energy. That is the lowest background, and this dominated. This is our next challenge. This event rate, which is shown in blue here, is dominated now from radon, from the radioactive radon, which is emanated by every surface in everything inside the target itself. And that's what we want to reduce by an order of magnitude with the xenon and ton. That's our main challenge for the next phase of the experiment. Maybe I want to make it shorter because, of course, the data, we have been taking data for more than 2 years continuously. We have published last year a ton-year exposure, the largest exposure ever used for dark matter search, from 279 live days of dark matter search from November 16 to February 2018. 1.3 ton of fiducial mass, which gives us this ton-year exposure. And we have done a blind analysis over several months, almost a year of time, in order to protect ourselves from bias. We've even added some salt. And so this is the blinded region. This is the response of the detector, the background rate. And what else? A lot of stuff. So what can I say? One thing that we had to understand is the response of the detector in terms of charge and light. I showed you some of the plots initially, but these parameters are very important to tell us. That enabled me to tell you how many photons, how many electrons actually a signal of photoelectron means. So we have measured this so-called G1 and G2 parameter very precisely through a large number of calibration data, or lines, if you like, that we detect in our detector. And one point just to make, in case somebody is interested, that this large detector, this is energy resolution, how precisely we measure the energy of an event in these detectors. And that's an important response parameter. And it's impressive that the energy resolution as a function of energy is shown here in this 1 ton detector, which is the largest ever built. That's the first scale TPC of this size, has an amazing energy resolution, and it's very good even in the energy region where neutrinoless double beta decay of xenon 136 occurs. So we have a very good detector in terms of energy resolution. We can map or reconstruct the position through a variety of algorithms. And so this is some of the calibration that we do for inferring the position of every event, which we know at the level of 1-2 centimeter. That's the precision in position. And most importantly, the goal of the calibration data that we take continuously interspersing the dark matter data is to measure the response of the detector to low energy particle, electronic recoil, and nuclear recoil. And we do that with a variety of sources, from radon to zero for the electronic recoil response. This is charge versus light, in simple words, calibrated with this radon 220 source. And above is the charge over light for a nuclear recoil, which we calibrate using americium beryllium as a neutron source, so a DD neutron generator, which we deploy in the water. That's a very important study, which enables us to know where our charge and light is before we unblind. So anyway, to make a long story short, so we then struggle months to understand all the background sources in the detector, predict the background, the number of background events that we expect from coherent scattering, from radiogenic, from electronic recoil, from surfaces. So we do a lot of modeling and understanding, and this understanding of the background enabled us to actually to choose the best fiducialization that I showed you at the beginnings to maximize sensitivity and response. Finally, after a long, long story, we finally opened the box. We unblinded. We knew how many events we would expect due to background. We opened the box. We see how many events fall in the region where dark matter should be. This is a plot of S2 over S1. If you like, just look at the left plot for now. The black dots are what we expect from electronic recoil from the background that we have in this detector, which is still very low. And then you have this other, with a pie chart next to it. We invented this idea to show these events. We give them a probability that they look more WIMP-like. So the larger the pie, the more WIMP-like it is. And you can see we find a bunch of events, but we are not ready to call them WIMP because a lot of them, and especially the three which have the largest WIMP probability, are very likely either a neutron-like event or a leakage from the electronic recoil band, or is maybe a surface background event. So everything together, and in fact, we can say that from this because we also can see them in Z, in space, and the largest three pie charts are actually excluded as real WIMP signal because they have too much probability of being a neutron or a surface. So finally, we do all this statistical inference with the profile likelihood and so on. The results of this blind analysis is consistent with a null hypothesis that we don't see any significant excess above 3 sigma, and therefore in this 1.3 ton volume, and therefore we can set the strongest 90% confidence upper limit on the spin-independent cross-section, reaching to a minimum of 4.1 times 10 minus 47 square centimeter for 30 GeV WIMP. And that's shown in this typical plot where the cross-section is shown as functional WIMP mass. Xenon 1 ton result shown as the most sensitive to date, and it remains like this so far. I'm running out of time. We are not limiting. We have done this last year. We have also probed spin-dependent coupling of WIMP, spin-dependent cross-section, and that's the best limit that we have derived. The paper is on the archive since few weeks, and in fact, this is the best limit for neutrons, WIMP neutron coupling, and we have done it also in a space where the synergy or the complementarity with collider search is picked up here with this isoscalar WIMP nucleon interaction with an axial vector mediator. So we can place a limit on this mediator. We also have studied the WIMP pion coupling, and many other searches are underway. So I want to tell in the few minutes I have left what next. What next? Because those searches which goes on, those studies go on, and they will give a wealth of new results, and we keep improving, placing constraints on a variety of models, of WIMP models, of dark matter models, actually. So what we are doing is to replace the Xenon 1 ton has stopped because we need to make space to this larger detector, which is an 8.4 ton detector. We go from 1 meter drift to 1.5 meter drift height, which has never been done, so we keep challenging ourselves. The key has been to enable this new massive detector in the same water muon Vito, in the same infrastructure that we built and very validated with Xenon 1 ton to make us go a bit faster. So mainly is the new detector that we're doing. And of course, a variety of the new TPC, which is a big challenge. We are building it now. At Columbia, especially, my group has taken the challenge of developing a liquid xenon purification system which handles the 8 ton in liquid phase. We cannot just waste our time in purifying the gas because it will take us too long to get there. So we are testing at Columbia, and we are building the purification system for the first time for a xenon detector which takes directly the liquid out of the detector and cleans it to appropriate filters and pumps. And another big challenge is the radon distillation column, because I mentioned that radon is our main challenge to tackle. And finally, we want to get rid of neutrons, even the miserable number that we expect. So we are adding a neutron veto to the experiment. And I will show just some picture because we're running out of time, essentially just reducing the background, the liquid xenon purification, and we're doing very well on this front, both at Columbia and Munster University, developing the radon column and the liquid xenon system. And with the Japanese friends and the Italian colleagues and German colleagues, we are developing this gadolinium-loaded water neutron veto to essentially reduce the number of neutron-like events to less than 1 in 20-ton-year exposure. That is the plan, and this will bring us to this. This is the final picture that I will show you. I mean, I can skip the other one. This is where we are going with Xenon, with the Xenon program, and you can see the impressive, in this plot, you can see Xenon 10 up there in 2007 or 8, Xenon 1 ton result from last year, and we want to get with 4 or 5 years, 3-5 years of data, depending on the fiducial mass with Xenon and ton. We want to get to the 10 to the minus 40, close to 10 to the minus 48 square centimeter cross-section, and hopefully find a signal. And here is the so-called neutrino flora, where the events from neutrino, and you also notice that neutrinos are going to be going to give us a non-negligible signal from coherent scattering at low energy, and hopefully at least that signal will be available to us. So I stop here because I guess the summary is not needed. We have a lot of science that we can do with Xenon and ton, or with the Xenon program and similar program which are coming up. The competition is very strong. In fact, we have competition in China, we have competition in this country with 2 similar experiments, also using liquid xenon. But of course, the goal has always been, at least for me, to be first, to be fast, and so that's what I hope we will manage to do. Thank you.